Hi, welcome to my talk on using trajectory data for improved region of attraction estimation. My name is Morgan Jones and I'm a lecturer at the University of Sheffield. Before beginning the talk, I would like to thank my collaborators that contributed a lot to this project, including Lucas, Daniel, Matthew and Louise. Many systems can be written as nonlinear ordinary differential equations, given by this equation in 1, defined by the vector field f. Such systems like power systems, weather models, and population models can all be written in this form. Given ODE defined by the vector field f in equation 1, we next define what the solution map is. We denote this solution map by rho subscript f. This is a map from initial conditions and time. The solution map satisfies the ODE and also at time equals 0 is equal to the initial condition. Moreover, we define the trajectory as the mapping from a fixed initial condition and time from t equals 0 to infinity. We define the trajectory as the set of this mapping. Unfortunately, unlike for linear ODEs that have analytical solutions that are based on the matrix exponential, there are no closed form expressions for the analytical solution map of a nonlinear ODE. However, they can be shown to exist using Picard iteration, and we can deduce certain properties about these solution maps, such as how differentiable they are. Moreover, given a fixed initial condition, we can approximately simulate the trajectories using many ordinary differential equations that are inbuilt in MATLAB. So the goal of this talk is to work out or approximate the long-term properties of the solutions to nonlinear ODEs. So given an ODE defined by some vector field f, we would like to work out what happens as time goes to infinity, either for fixed initial conditions or initial conditions inside some set. Given an ODE defined in equation 1, the goal of this project is to approximate the region of attraction. The region of attraction is the set of initial conditions such that the solution map tends towards the equilibrium point, which we assume to be the origin under the Euclidean norm. The problem we're trying to solve is to find the set S such that the set S is a subset of the region of attraction and also roughly equals the region of attraction. A naive way to approach solving this problem is to use ODE solvers to approximately simulate the trajectory for randomly sampled initial conditions and show that for sufficiently large time these simulations get within some epsilon of the origin. However, this naive approach is not the best way to solve the problem because there may be uncountably many initial conditions, there's error in the simulation, and we don't know how large of a time we should be simulating the trajectories to show stability. So we're going to try and solve the problem still using trajectory data, but going about it more indirectly by using the trajectory data to approximate something that's called a Lyapunov function that should give us a set S that's a subset of the region of attraction and also roughly equals the region of attraction. So it is well known that we can approximately estimate the region of attraction by finding Lyapunov functions and looking at their sublevel sets. A Lyapunov function is a function that is positive and 0 at the equilibrium point, which we assume is the origin, and also decreasing along the solution map, which amounts to 0.2 here, that is a differential inequality. If we can find such a Lyapunov function and a scalar b that is positive, such that the b sublevel set of the Lyapunov function is contained within its domain, then this sublevel set provides an inner approximation of the region of attraction. However, we don't know how good this approximation is. So the converse Lyapunov question is, given some assumptions about our ODE such that it is exponentially or asymptotically stable, can we show that there exists a Lyapunov function that can certify this stability, and also can we show that this Lyapunov function can yield an arbitrarily close approximation of the region of attraction? We next look at some common converse Lyapunov functions that we know to exist, and they're based on the solution maps that we know exist from Picard iteration. Arguably, the most commonly used converse Lyapunov function is the maximal Lyapunov function that was first proposed by Masera in 1949 and later analyzed by Vanelli in 1985 in regards to regions of attraction. The converse Lyapunov function is based on the solution map and takes the form of an integral from 0 to infinity with the solution map squared. This form is a simplified version of what was proposed by Masera because here we're going to assume exponential stability. And if the system is known to be exponentially stable, then this maximal Lyapunov function gives an analytical solution of the region of attraction as the infinity sublevel set. However, this maximal Lyapunov function is unbounded outside of the region of attraction. It takes values of infinity. This can make it hard to approximate, especially if you're trying to approximate these converse Lyapunov functions using continuous functions. In our previous work in last year's CDC, we proposed a new converse Lyapunov function that's a modification of this maximal Lyapunov function and is a lot closer to a converse Lyapunov function proposed by Zubov in 1964. And it involves the exponential of the maximal Lyapunov function. And we can see that this converse Lyapunov function takes a similar structure to bump functions in analysis. So intuitively, we can see that they should be quite smooth and differentiable. And also, they are globally bounded by 1, because when this integral of the solution map is infinity and we're outside of the region of attraction, we have 1 minus e to the power of minus infinity, which just equals 1, so they're bounded by 1. So in this box, it's our converse Lyapunov function again. And in our previous work from last year, we showed that the 1 sublevel set of this converse Lyapunov function equals the region of attraction. And if we assume the system is locally exponentially stable and for well-chosen parameters alpha and beta that appear in our converse Lyapunov function, we can show that this Lyapunov function is Lipschitz continuous. And also we can show it satisfies a PDE. So the first 2 bullet points, the fact that it characterizes the region of attraction and is Lipschitz continuous, makes this a good converse Lyapunov function for approximating. The PDE property we used in our previous work to build a sum of squares algorithm for finding the region of attraction. So given our converse Lyapunov function, we can now simulate the solution map using an ODE solver to generate input-output data about this Lyapunov function. So through experiments or just numerical simulation, you can generate a data matrix, Dij, which is the Euclidean norm of the solution map initialized at certain initial conditions xi and at certain time steps indexed by j. Based on this data matrix, we can approximate the value that's outputted by our converse Lyapunov function by approximating the integral using some sort of Riemann approximation and then substituting this integral into our converse Lyapunov equation. So then the problem of finding this converse Lyapunov function becomes a supervised learning problem where we have some input-output data and we need to use an appropriate learning algorithm to find a model, and this model will be our converse Lyapunov function that fits the data very well. So there are many machine learning algorithms, and we will look into these in future work, but for this talk we're going to focus on Bernstein polynomials because they have some nice theoretical properties about them. So the equation for a Bernstein polynomial is given in this box, where we need to know the value of the function we're trying to approximate at certain grid points, and we multiply these values with Bernstein polynomials and sum them up. So to compute the Bernstein polynomial of some function v, we only need to know the function at certain grid points, which in terms of the converse Lyapunov function, we can find using simulated trajectories. The Bernstein polynomials have a nice property that they uniformly approximate the function v in the derivative as well as the zeroth order. So this is done uniformly. So this is important when we're trying to approximate Lyapunov functions, because we have the property that they are decreasing along the solution maps, which amounts to this differential inequality given in 2. So we'd also need to approximate it in terms of the derivative in the hope of satisfying 2. What's interesting is that the Bernstein polynomial actually only takes zeroth order data, but is able to approximate in the Sobolev space, so approximate the derivatives, as many derivatives as the function is smooth, which is an interesting property of Bernstein polynomials. So here is a slice of our state space xi, and we've plotted what v dot of our converse Lyapunov function could look like. So it's negative everywhere and 0 at 0. So if we approximated this function uniformly, by v tilde, which is this red function, say the uniform approximation is within epsilon of our converse Lyapunov function, we could end up with this sort of plot for v tilde dot, our approximate converse Lyapunov function. And we see that because the converse Lyapunov function v dot equals 0 at the equilibrium point, which we assume is at the origin, we expect some small neighborhood of the origin to be also potentially positive when we're looking at our approximate converse Lyapunov function. So this means that even with uniform approximation, our approximate converse Lyapunov function may not be a Lyapunov function itself. So we can't use it by itself to approximate the region of attraction. But as we'll see on the next slide, what we're going to do is we're going to combine it with a already known Lyapunov function, but maybe this Lyapunov function only certifies a small neighborhood of the origin as stable, but this is enough to use this in combination with our approximate converse Lyapunov function to improve the region of attraction. So given some ball of radius eta, we would like, if we could find two functions, v1 and v2, such that v1 is our approximate converse Lyapunov function with a sublevel set given as gamma 2 that contains this ball of radius eta, and another sublevel set of gamma 1 that's contained within this ball of eta, such that v1 dot is less than 0 between these sublevel sets. So if we initialize our solution map between these sublevel sets, then because v1 dot is less than 0, it should decrease and move towards the smaller sublevel set and hence transition into this ball of radius eta. Then if we can supplement v1 with analytical Lyapunov function, whose sublevel set contains this ball of eta, then once we get into the ball eta, then the analytical Lyapunov function v2 fully certifies the stability, and we can combine our approximate Lyapunov function v1 with the analytical Lyapunov function and take the union of their sublevel sets. So that's the union of the outer sublevel set and the black sublevel set, this region, to improve the region of attraction, which would be hopefully larger than just the region of attraction that the analytical Lyapunov function v2 gives. So we would find v1 by approximating our converse Lyapunov function using Bernstein polynomials, and v2 can be found using physics, so the energy functions of a nonlinear ODE, or by linearizing the ODE and solving an LMI to find a quadratic Lyapunov function, or by using summer squares programming to find a analytical Lyapunov function. So for benchmarking purposes, we did this for the van der Pol oscillator, which is given as this nonlinear two-dimensional system. We approximated our Converse Lyapunov function from the trajectory data using a 75-degree Bernstein polynomial. And we also used for V2 a quadratic Lyapunov function found by linearizing the system and solving an LMI that we found in a textbook, and that's given here. So the quadratic Lyapunov function only provides this small region as the region of attraction, whereas the V1 Bernstein approximation can extend the region of attraction and actually fully contains the sublevel set of the quadratic Lyapunov function. The green region is the true region of attraction that we found using Monte Carlo simulation for benchmarking purposes. Here's a second numerical result where we looked at this machine infinite bus system that has a non-polynomial vector field, and we looked at using a 60-degree Bernstein approximation of the Converse Lyapunov function together with a known analytical energy function that's given in this box. And together, the union of the two sublevel sets can be shown to be a subset of the region of attraction, and this is improved upon just using the energy function alone. We also looked at higher dimensional systems like this 4-dimensional two-machine system, and in the diagram on the left we looked at a 2-dimensional slice of the state space, where again we've found the region of attraction as this green curve using Monte Carlo simulations, and we used a 20-degree Bernstein approximation and an analytical Lyapunov function that was found using summer squares programming from elsewhere in the literature that's given in this box, and together we were able to improve the region of attractions by taking the union of the two sublevel sets here. And we also found similar results for the A3 machine system, which is still a 2-dimensional system, using a 20-degree Bernstein approximation and an analytical Lyapunov function found from the literature.